33. A man can throw a ball a maximum horizontal distance of 191 meters. Now, there's something that I probably should have mentioned. I didn't really mention this other than when someone mentioned it in class, the range equation, but there is an interesting factoid associated with it. And, you know, we already said, if you look at this equation, when theta is very small, you're throwing almost parallel to the field, it's not going to go very far. When theta is close to 90 degrees, it's not very good. Well, somewhere in between there is the best angle. When is this maximized? Well, you can see that just by looking at it. As you're changing the angle, but throwing with the same initial speed, assuming you can throw at the same initial speed, but you want to know at what angle to release it, the only thing that's changing is this. And what's the biggest sign can be? Well, 1. It goes between +1 and -1. The biggest sign can be is 1. When is the sign maximal? Well, it's when its argument is 90 degrees, right? The sine of 90 degrees is 1. If we draw the sine function, it looks like this. And here is 90, here's 180, and so on. So that's like sine as a function of the angle or the argument. So it's when this thing is 90 degrees. 2 theta is 90 degrees, and that means theta is 45. So in the absence of air resistance, when you're throwing something with projectile motion, if you can ignore air resistance, then the best angle to throw it at if you want to get the most horizontal distance is 45 degrees. And so we're going to use that fact here. Person can throw a baseball a maximum horizontal distance of 191 meters. So the assumption here is the person's taking advantage of the 45 degrees and throwing it at that angle. So the picture would be and the 191 meters is probably just in my version of the problem. So the picture looks like this. Here's our horizontal field. This angle is 45 degrees. With some initial speed, I don't know what it is, but in any case, when they throw as hard as they possibly can, in my version, 191 meters. To me, that sounds ridiculously far. I certainly couldn't throw that far, but they give a range for which the random numbers can go, and maybe this is at the high end. I don't know if anyone is a baseball player in here, but that's what, you know, a football field is 100 yards, 100 meters is a little bit bigger than that. And we're saying, you know, probably about 2 football fields to throw. I don't know. Maybe with the right ball, a very dense, small ball, you might be able to do it. I don't know. How far can the same person throw the same ball vertically upward from the ground? Assume the ball is thrown from the ground and that his muscles give the ball the same initial speed in each case. So this person throws as hard as they can. They have some initial speed that carries the ball 191 meters when they release it at that best angle. Then the question is, if you throw it with that same speed, V0, vertically upward, what is that maximum height it goes to? Okay, so how might I start this problem? And again, we have the range equation to work with. If I look at the range equation, what do I know in it, and what is it going to allow me to calculate? Yeah, I know how far it goes. That's the 191 meters. And we're assuming theta is going to be 45 degrees here. If it's the maximum, the person's really taking advantage of the best angle to throw it at. So what that is going to tell us, this isn't going to answer the question for us because we really want a height, but it's going to tell us something interesting. 191 equals V0 squared times the sine of 2 times 45 degrees. That's the sine of 90 degrees. The sine of 90 degrees is 1. So I'll just put a 1 up there. Divided by little g, which is 9.8. And therefore, V0 is the square root of 191 times 9.8. Okay, that's interesting. Let's go and now think about how we might calculate this, because if I know that initial, obviously bigger initial speeds will give me bigger heights, so it seems like I need to know that initial speed. So now let's address the problem at hand. If you throw a ball up with this speed, I can calculate that number by putting little g as 9.8 in there. How high does it go? What kinematics equation, we've got them conveniently written over here, would we use there? Given that we know the initial speed, I mean, I guess, yeah, I would choose the third one as well. I haven't given a axis direction, but let's take plus y is up. I think it's pretty clear. I want to take initial to be release time and the final to be the highest, and that will involve that height h. And if we look at the third one, just written in terms of y, Vy final squared equals Vy initial squared plus 2ay delta y. And that delta y is, that's how high it goes up. So I'm just going to relabel it here as h. The displacement will be h. It's going to be positive. What's Vy final? It's 0, right? It's at the highest point, so it's not moving in the y direction at all. Vy initial is, well, it's the square of this, so it looks like 191 times little g when I square that thing out. Plus 2 times minus little g, right? Ay in my coordinate system is minus little g. It's h. So it looks like I can divide both sides by little g. Because when I do 0 divided by little g, it's still 0, right? If you multiply or divide 0 by anything except 0, you don't want to divide by 0, but little g is not 0. So the little g cancels out. And it looks like h is equal to minus 1, h is equal to 191 over 2, half of that distance, half of the 191, if I did that correctly. In any case, that's how to approach it. The range equation, otherwise it's a huge pain to figure out how to work that 191 in there to back out what the initial speed is. But using the range equation, it's pretty easy. Any more on this question? I think that was just a one-part, just a one-part question. Anything else on the homework? Ones that you don't know how to get started on? Yes, Anna?
I wasn't really sure how to get 37 started.
37 says the following. There is a building, and we're tossing something off the edge of the building. So here's the building, here's the ground. We don't know the height of the building. In the diagram, it's labeled as just h. But something is tossed at an angle off the building, follows a parabolic path, and we're told in my version that from right below the edge, right where it was released, to the point where it hits the ground is 17.9 meters. These are my numbers. And also my numbers, it's released at 10.6 meters per second at an angle relative to the horizontal of 52 degrees. We're given the mass of the rock, but I don't think we need it because mass doesn't come into any of our kinematics equations. We already know you throw a light object, as long as air resistance is negligible, a small ball or a big ball or a big rock, all will follow the same arc path, and they will go just as fast, so it doesn't really have to do with the mass of the object. I think that's all the information that's given. And the question is, how tall is the building? Assume the ground is level and the side of the building is vertical. They're telling us in every problem almost the acceleration of gravity is 9.8. Well, occasionally you'll have an author put a 9.81 in there. And because the little g depends on where you are on Earth, someone might have written a problem that assumes little g is 9.81. And if you're using 9.8, that would cause you to be numerically off a little bit. So you do have to pay attention in the homework just look at that little g value and say, is that the one I'm using? If not, I might have to change it to 9.81 if somebody chose to use that, since it's not an absolute number. How tall is the building? What's h? All right, so I've got some information about the horizontal distance in between here and here, and I want some information about the vertical distance. How might I proceed? Yeah, certainly we're probably going to want Vx initial and Vy initial, and I'm not going to calculate them in my calculator, but Vx initial would be 10.6 times the cosine of 52 degrees. Vy 0 is equal to 10.6 times the sine of 52 degrees. And hopefully that is something, that's a little bit of trigonometry we're doing over and over and over again. Hopefully it's becoming second nature. If it's not, definitely, if you need an explanation of that or you're not sure why one is cosine and the other one is sine, let me know. Okay, that's something I'll need. How am I going to get h? Maybe the best, if you want a problem-solving technique for this, I usually say, well, what do I want? I want to grab an equation that has what I want. Now, I may not be able to get it in just one step, but at least it will tell me what other things I need before I can get at that. So, what equations? Well, I guess I need to decide on a coordinate system. Doesn't really matter what coordinate system you choose. You could choose one down here or even up there. I'm probably going to choose one down here so the origin is right on the ground below where it was released. Plus y is up, plus x, the horizontal direction it's going. The only reason is if I put my coordinate system up here, then y final would be minus h, which seems a little bit awkward to put in. This way, everything stays positive, right? It's all above the x-axis. Okay, so I want to choose a y equation to find h. And I have two choices if we translate this into y. I have one that involves t, and this one would involve a delta y here. And delta y, if I take my initial to be the throwing point and the final to be hitting the ground, the delta y would actually be minus h in my coordinate system, right? Because it's gone down in y coordinate there. Anybody have any preference to which one we use here? The third one. Okay, so let's try that. Vy final squared equals Vy initial squared plus 2ay times delta y. Let's plug into it. I don't know Vy final, and I don't want to know it, but I just got to leave it in there as a symbol right now. In other words, how fast is it traveling in the vertical direction right before it hits the ground? I don't have any information right away, but maybe we'll be able to figure it out from something else. Vy initial, we already said, I'm just going to kind of circle this. We know that, so just we can calculate it. It's the square of the number we put up there. Plus 2ay. We know how to calculate that. In my coordinate system, ay is minus 9.8 times delta y. So the things I've circled, we know how to calculate. I could get delta y, and delta y I'm expecting to be negative, so whatever number I get for delta y, that would be the negative of h, how high the thing is, right? Because delta y is going from a larger y to a smaller y. That's a negative displacement. All right. How then am I going to get Vy? Yeah. I don't know. Maybe I don't think we've run into a dead end. You can always sort of squirrel your way through the equations if you think hard enough. Now, the only other equation that's going to involve a Vy final is going to be this one up here. So I could use this equation to trade out a Vy final for t. Maybe that's better. All right, let's just try substituting that in there. Okay, hold on to that. Vy final is equal to Vy initial, that's something we know, plus Ay times t. I know that. So I could substitute this thing in there and square it all out, right? And then this would be written in terms of t. Now it's going to be a quadratic equation because I'm going to be squaring out here something plus something times t. And when you square out that, you're going to get a t squared term, and you're going to get a t term, and you're going to get a constant term. So it looks like if I only knew t, I'd be done, right? I'm going to have this in terms of t, or you can think of it this way. If I only knew t, I could get Vy. I plug it in there, and then I get delta y, and then we're done. That's one way to think of it. How now can I get t? Yeah, I haven't used the 17.9 meters yet, so let's go with the x equation versus t because we want to know t. X equals x0 plus vx0 times t plus 1/2 ax t squared. It looks scary, but it's not really because ax is 0, so it's just a linear equation, not a quadratic equation. In my coordinate system, this is 17.9. x0 is 0. It starts out at the origin. And then Vx0, we know. We're just going to circle it, times t. So I can solve for t if I plug those numbers in. If I've got t, I can get Vy from this equation. If I've got Vy, I can get delta y. Now we are doing this in 3 steps here. Does anybody see how we could have gotten away with just 2 steps in this problem? I don't think you could do a one and done, but how might I have gone about it a different way from the beginning and just gotten a relationship between the y I want and t to begin with, rather than a relationship between y and Vy final and Vy and t, and then x and t? We could have used this, but with the y's in it, right? That would have given me automatically. What I want to know is, in my situation, well, let's just write it down. Y equals y initial plus Vy initial times t plus 1/2 ay t squared. Y final is 0. Again, I'm taking initial to be here and final to be down there. Y final is 0. Y initial is h. Vy initial, we know how to calculate it, times t, plus 1/2 ay, I know how to calculate that, times t squared. And that equation, that relationship that tells me how to calculate h if you only knew t, is going to be the same as if I went through the painful process of taking this and substituting it in for Vy there and squaring it out and making a big mess, and I simplified it. It would just look like this equation. So we're really kind of making a little bit more work for ourselves here. But, it illustrates the fact that there are several ways you can go through these equations to get to the final answer. We want to try to, at least think, what do they call that? Metacognitive thinking or meta something. You want to think about the process. How am I going to make my choice rather than just, at the beginning you just kind of randomly choose or say, I'm going to choose anyone that has the variable I'm looking for. But sometimes there are better choices. Any more on that question? That was also a one-part question. Anything else on the chapter 3 homework? Andre? Yeah, sometimes you have to kind of think hard to get at what they're saying. I think all of them are phrased. Yeah, okay, so let me just read the statement of the problem here. This is a 2-part problem. At the beginning it says, a particle has an initial horizontal velocity of 2.8 meters per second and an initial upward velocity of 4 meters per second. It's given a horizontal acceleration of 1.7 meters per second squared and a downward acceleration of 1.2 meters per second squared. So if I choose a coordinate system corresponding to horizontal and maybe up or down, it doesn't really matter, then I could figure out what Vx0 and Vy0 are in my coordinate system, and Ax and Ay in my coordinate system. And presumably that acceleration is constant after that period, otherwise we have no idea how to do it. What is the speed after 2.4 seconds is the first part, and the second part it says, what is the direction of its velocity at this time with respect to the horizontal? You know, so the idea is, well, let's just move this over here. So the idea is, you know, I choose some coordinates, and maybe I choose my x to be the horizontal direction and plus y to be the vertical, you know, upward in the vertical direction. And we've got a particle, we don't really care where it starts at, but it's given an initial velocity x and y component, and then it accelerates for a while. And for example, I don't know how all the answers work out, but I might find that after that so many seconds, in mine it's 2.4 seconds, maybe it's going like this, and I find out that Vx final is 3.3 meters per second, and I'm trying to make it look like that, maybe. Looks like it has a positive x that's bigger and a negative y component that's a little bit smaller in magnitude. When they say, what is the direction of this velocity at this time with respect to the horizontal, what is meant is, what is this angle? Except, you know, or if my thing were up here, it would mean, what is this angle? If it were going in this direction, it would mean, what is this big angle right there? It wants an answer between minus 180 degrees, so that would be things almost over there, to 180 degrees, so it can accommodate any angle, any direction that it's going. And in this case, how could I find that angle? Yeah, it's always true that the tangent of that angle, no matter which way this is pointing, is equal to the y over the x components. The units would cancel out. Vy over Vx. What I have to think about is then, is theta equal to the inverse or arctangent of that number? Well, in my case here, for the original one that I drew, forget about these, do I have to add the 180 degrees onto that result or not? No, if your vector that you're trying to find the angle for is either pointing down into the quadrant 4 direction or up into quadrant 1, anywhere with a positive x component, you can just use the arctangent. It's when it's pointing over here anywhere that you've got to add the 180 degrees onto it. And so in this case, the output of that inverse tangent is going to give me a negative number, small negative angle. I just made these numbers up, but if it were pointing over in the other case, you might have to say, well, I got, you know, if it's pointing over here, and that would be one of the most difficult cases, right? If it's pointing over here, you would be getting the positive angle that's here. If you add 180 degrees, you're going to get an angle that's not between minus 180 and 180, and you're going to have to think about it for a second and think, well, how can I rewrite that angle as an angle between minus 180 and 180? And I bet you can all do that. I don't know, maybe they restricted it so they all end up between minus 90 and 90 to make it easier. Anything else?
Angle or the x displacement, and I was using the tangent of the opposite over adjacent. It was the wrong answer.
I mean, the only way I can really help you with that is to look at your particular problems and what you're putting into it. So it's not something that we can really talk about as a class, but if you want to look at it right after class is over, it's certainly fine. Okay, good. Well, let's then go back to, I don't think there's anything else I wanted to talk about before we jump back into chapter 4, which is really at the heart of the physics. And it may seem like, oh man, we're just constantly doing something so different than what we've done before. You're going to find that the themes we've developed in chapter 4 and also the stuff we learned in chapter 3 and chapter 2 continue through the rest of the course, and we're not just going to have new method for solving problems after new method. They're going to sort of continue to be that theme of a lot of Newton's second law and things like that, as we just consider it in different contexts. So, for example, in chapter 5, we're going to talk about objects in uniform circular motion, things that are going in a circle at a constant rate. Applicable to orbits like the moon is almost going in a circle at a constant rate around Earth. Earth is almost going in a perfect circle around the sun. And so it's a very good approximation there. Now, in that case, the acceleration isn't constant, right? The velocity vector is changing all the time. And the acceleration vector is actually going to be changing direction as time goes on. We'll find out. So we have to use some different techniques, but we will be using F net equals ma again, over and over again throughout the course. All right, let's see where we are here. Oh, I guess I have some reading response questions that maybe I thought were throwbacks to the stuff that we had been doing. And so let's take a look at 2 of these. Can we talk briefly about the logistics of our example? Yes, we did that. How would the force of gravity and the normal force not be equal and opposite in terms of Newton's third law? So we see a lot of situations where an object, let me grab my generic mass here. Here's a mass sitting on a table. Gravity's pulling down on it. The table's pushing up on it. If the table weren't pushing up on it, it would be in free fall. It would just burrow through the table. It doesn't do that. In this case, how do I know that the normal force, that upward force from the table, and the gravitational force going down have to be exactly equal and opposite? Why is that? Because it's not moving, right? The sun, those are the only 2 forces I can think that are on this. You know, it's horizontal, so it doesn't really need a friction force to keep it from going to one side or the other. So the only forces that are on it are the upward force from the table and the downward force. It's not accelerating, so the sum of the forces must be 0, and that means these 2 force vectors have to exactly cancel each other out, or they add to 0. And it's hard to see that with the parallelogram method, but you could do the tip to tail, right? If you go down and then you go up by the same amount, you'll end up with a vector that has 0 length. So it's not accelerating. In that case, the normal force balances out the weight force. Is that always true, that the normal force balances out the weight force? I think that's what's being asked here. Maybe the book mentioned that that might not be true. I'm not sure where the question came from. How could I make them unequal? I could certainly push on it. That would be one way. Now I've made 3 forces, so those 2 alone don't have to balance out. Now the 3 have to balance out. Another way I could do it with some, drop it, certainly, and in that case, well, there's no normal force, so it's a little bit confusing, but I could do something that's almost like dropping it. I could take the surface it's sitting on and cause it to accelerate upward, right? So it's at rest and it starts going faster and faster upward. Why does the normal force not balance the weight force there while it's accelerating upward or while it's accelerating downward? I mean, there still is a normal force, right? It's still pushing up from the bottom. There still is a weight force. How do I know that they don't balance out if I start accelerating it upward? Because it's accelerating. If there's an acceleration, Newton's second law says the forces can't balance. And so a lot of, a mistake that a lot of introductory physics students fall into is thinking, we see an awful lot of examples where forces balance out. But that doesn't mean they always balance out. And whenever something's accelerating, it means the forces don't balance out. So that's another way to make them not equal. If you make the table cause it to accelerate up, or you maybe partially let the table start to fall and accelerate downward, and then the normal force would be less than the weight force. The weight force has to win out to cause it to start accelerating downward. Okay, onward. This is stuff I think you maybe watched in the video before yesterday even, but we're sort of going in a weird order through the chapter, but we'll hit all the highlights that Giancarlo does. The worksheet problem that was done, this is not on our worksheet from class, but rather one that I was working my way through in the video. And it has to do with two objects connected by strings. So there was a little discussion about properties of strings and what tension means. So here, just for example, here's a mass hung to a mass connected by strings and connected to the ceiling or something. That might be a typical problem we might want to analyze. And we're going to consider the simplest possible kinds of strings. We're first of all going to assume, and we're never going to relax this assumption in physics 110, although you certainly could make it not true in a more advanced physics class, that these strings themselves have a totally negligible mass. So compared to the masses that they're connected to, we can just treat the string as having zero mass. We will always make that assumption in physics 110. And I don't care if it's labeled as a cable or a cord or a string. We're just going to always assume that they're essentially massless, even though a cable sounds pretty heavy. We're also, since that's true, then what is going to be true of these is that the strings have what's called a uniform tension all the way through them. If you have so the tension means how much the string is trying to be stretched taut. Strings and cables and things can't support any pressure, but they can support tension, right? You can pull on the two ends, and the harder you pull on the ends, the more tension you're putting in. I'm just appealing to your intuition. We'll talk about what tension means in just a second. Now, if I hung a very heavy or massive, dense cable from the ceiling here, you can imagine that might not be true for that cable, because just above the bottom of the cable, it's only got to pull up hard enough to keep that little bit at the bottom from falling down. Whereas at the top of the cable, it's got to pull really hard, where the metal is connected to the metal in that cable. It's got to pull really hard to hold that whole heavy cable down below. And so the force required to hold it up is going to get bigger and bigger as you go up. But if it's effectively massless, we're just going to say it's the same all the way through. So the tension doesn't vary all the way through. And what does the tension mean? It means, practically speaking, when we have a string like this, whatever it's connected to at the two ends, it pulls on those ends inward along the direction that the string is connected to the end. So, if the string is connected off in this direction and someone's pulling on it, it would pull in the direction the string goes. And the tension tells it how hard it pulls on the two ends. Since it's equal on both ends, it's the tension is just, so the tension is in units of force. So this tension might be 3 newtons. That means the string is pulling down on the ceiling with 3 newtons, and it's pulling up on this block with 3 newtons. Maybe this tension is 5 newtons. That means it's pulling down on this block with 5 newtons and pulling up on this block with 5 newtons. So that's how you use tensions. It's just a different way of specifying a force. And it always acts along the direction of the string. When all those assumptions are being made, especially that it's massless, we sometimes just say it's a light string. Light meaning not heavy. Okay, and then I'm not going to go in detail through this problem, but I want to point out one key thing that's going to be important for the worksheet problem that we will turn to in just a second, a slightly different one. So here is someone pulling on a light string, applying a force of 5 newtons in that direction to the end of this light string. Now that string is connected to a 1 kilogram mass, which is connected via a string to a 2 kilogram mass, and they're all on a frictionless table because we haven't really talked about friction yet, so we're just going to ignore the friction here. It's like wet ice. Everything slides really easily. Which block has the larger acceleration? There was a discussion of this in the video, but what do you think? Why block A? Okay, so if it's got a smaller mass, it's going to accelerate faster, right? If I push on a 3 kilogram mass and a 5 kilogram mass with the same force, that 3 kilogram mass is going to accelerate faster because it's lighter. Now, somebody else gave a different answer. I'm not saying that response is right. They're the same. And what was the argument for saying they have to be the same? Yeah, they're essentially moving as a rigid unit, right? They may as well be glued to each other. Now, they happen to be connected by a string to each other, but it's sort of like, I think of this as one mass, but I could conceptually divide it down the middle and say, if I push on, maybe I divide it into 1/10 on this side and 9/10 on that side, so they have vastly different masses. And I put it on a frictionless table and I push it and it starts accelerating. I say, which half has the larger acceleration? Well, they're the same acceleration because acceleration is the rate at which velocity is changing. And at every instant, their velocity is exactly the same. So the rate of change of their velocity has to be the same for both of them. That's confusing usually to most people. So that's not supposed to be a trick question, but it's an important question to realize. When things are moving as a rigid unit, even though they aren't rigidly connected, the way they're moving is as if they're a rigid body, right? Because that string is staying taut the whole time. I should also mention, we're going to always assume that the strings don't stretch. So they're not like elastic strings that are bungee cord-like. They're supposed to be really rigid strings that don't, as you start putting attention in them, they don't get longer. So when we want to find the acceleration of block B, I could just as well find the acceleration of block A and then assert, well, it's got to be the same as B. They have the same velocity at every instant in time, and that means their acceleration is going to be the same. Or how did I approach it? I didn't do that in the video. What did I do instead? I combined the two into a single object. Not only are these two, since they're moving as a unit, they may as well be connected by a rigid rod, and we can think of them as one unit. I'm applying a force to that rod, and it's starting to accelerate. It's a 3 kilogram object. I'm welcome to think about them as a single object as long as they're moving as a rigid unit. That wouldn't really make sense if they were doing their own thing, but since they're moving as a rigid unit, it's kind of like, oh, do I want to conceptually divide this in two or think of it as a unit? Well, it doesn't really matter. If I'm trying to find the acceleration, it's probably simpler to lump it all together, and we'll find that that's true here. So lumping them together, I'm just going to, to remind myself what I'm thinking of. Here's my 3 kilogram mass. What's the free body diagram for it? Well, there are several forces that are on it. I've got it, when I'm lumping things together like this, I should always look at what are the forces that are reaching in from the outside and pulling on that object. I'm not concerned about the internal forces. There is a force of this string on the 2 kilogram mass, but that's a force that's in the middle of this object. It's sort of like with this mass here, in analyzing its motion, I never worry myself about the force that the left half exerts on the right half. Even though there is a force, right? That's what's keeping it together and moving as a unit, but I don't have to worry about calculating it. When I look at the forces on this object, I'm only looking for things reaching in from the outside and pulling on it externally. I don't care about parts of it exerting on forces on the other part. You can kind of think, well, these forces would cancel out anyways, right? This one's pulling in that direction, this one's pulling in that direction, but they're all on the inside, so we only care about the outside forces. So if we conceive of this as a whole, there, of course, is a weight force going down, mg. There's some normal force. And there's a 5 Newton force, essentially, pulling it to the right. And no forces pulling it to the left because there's no friction on the plane. If there were friction, friction would be pulling back in the opposite direction it's going. So this is what the free body diagram looks like. If I choose plus x in this direction, I could do the sum of the force x ax. What's the x component of this force? 0. 0 still, so that's easy. The only thing that I have to add up is this 5 Newton force, and it's a positive x component. Everybody see how to do that? We're going tail to tip. We're moving along the plus x direction, so it comes in with a plus sign. The other two are 0 x components, so I'm not even going to write them down. That's equal to the mass of the thing in the free body diagram times the acceleration. And then, so therefore, A in SI units would be 5/3 meters per second squared. That's the most important part of this problem, but let's just quickly flip through the other parts. Any questions about that, lumping it together? So what I found is the acceleration of the composite object, but now I can just assert, oh, that's the same as the acceleration of this object or this object. It's just the easiest way to get at it is think of it as one big unit and only look at the outside forces that are pulling on it, rather than this internal force, which is between two parts of the object. Okay, so both are the same. There's the process we just did. 5/3 is 1.67. How does the force of string 1 on block A compare with the force of string 2 on block B? A lot of people, sometimes when I've done this in the class, with the class before, a lot of people think they're about the same. They're not the same in this case. You can think of this string has to pull hard enough on this, and however hard it's pulling, that's the tension in the string. That's what we just said. The tension is how hard it's pulling on the edge. This string has to pull hard enough on this 2 kilograms to accelerate it at the rate we just calculated. This string has 3 kilograms sitting behind it, so it's going to have to pull harder, and that means the tension in this string is going to be bigger than the tension in this string as it's pulling. And we can calculate them. The tension in the right string, which is labeled as string 1 here, is the easiest to calculate. That's the question C there. What's the tension in string 1? It's 5 newtons, and that's because, look, the tension means how hard it's pulling on something. I'm pulling on the string with 5 newtons of force. So Newton's third law says that the string is pulling on me with 5 newtons of force. And by definition, that's what the tension means. So the tension in the string is 5 newtons. It's just a different way of telling you the tension in the string. Whereas for string 2, we're asked later on, what's the tension in string 2, and how do we get at that? Well, I can't use the 3 kilogram combined mass where I conceptually put them together because string 2 isn't an external force that's reaching in and pulling on it. So I have to use a free body diagram where string 2 is going to appear as an external force reaching on my object and pulling it from the outside. So I have a choice. It's pulling on both the 2 kilograms and the 1 kilogram. Maybe the 2 kilogram is a little bit simpler because the kilogram only has one horizontal force tugging on it, whereas the 1 kilogram has one on each side. So it just seems like I'm making my life more complicated if I choose the one. But either one would work out. So if I go down here and calculate the tension in string 2, this is what the free body diagram looks like for the 2 kilogram object. It's got the normal force, it's got the weight force, 2 times 9.8, but it's also got the tension in string 2. I just labeled that as T2 there, going to the right, and nothing pulling on it to the left. There's no friction, so there weren't any other forces. And then I do F net x equals MAX, and the only force with a non-zero x component is T2. And so the MA just gives me what that T2 is. Okay? The other two were about force components. And with force components, the x component of string 2's force on box B, string 2 is pulling on box B to the right. That's plus x for the decision I made there. So that's going to be a positive force x component. In the last question, string 2 is pulling on box A to the left, right? When it's tense like that, it pulls inward from the outside. That's how strings work. And so this is going to be a negative force x component. The number is just going to be the tension. You got to put a minus sign in front of it. Okay. There's a lot contained in that, but a lot of good practice problems. Here's one tension question, and then we'll do several practice problems on the worksheet that you have. Is tension a vector? Does it have directionality, or is it a scalar? And how does it differ from force? Well, when we say tension, we could treat it either as a force. Usually we're treating it as a scalar, right? When I talk about the tension in this string here, there are two forces associated with it, right? There's one going in that direction and there's one going in that direction. So if I give you the tension, I'm probably treating it as a scalar. But it also allows us to calculate two vectors, and those vectors are always directed along the direction that the string is pulling on the object. So you could treat the tension, or at least it's directly related to two forces. Okay, and it doesn't differ at all from a force. It has units of force. The only thing is there are different forces depending on which end you have it connected to. Okay. Let's look at problem. We're still working our way through the worksheet that you had from yesterday. Oh, and I just realized I didn't take roll today. Oh, that's not the one I want. Problem 6, 7, and 8. Apparently, they all have strings involved. Let me make sure of that. Oh, yeah, 6 involves something hanging from a cord in an elevator. So it's kind of combining our elevator thing we did yesterday with a string kind of thing. 7 is very similar to the problem we were just looking at. It involves a bunch of different masses connected by cords hanging from an elevator as the elevator is moving and accelerating. And maybe we can do problem 8 together. So why don't you work on problem 6 and 7. There's not too much calculation to be done in 6, even though it may take a while to wrap your brain around it. So in a couple of minutes, we'll stop and review 6 together, and you can tell me how it went, and then we'll spend a little bit more time on 7, because there you have to do 3 separate calculations. Don't forget your free body diagrams. I always start these problems the same way. 1, free body diagram. 2, axes. 3, F net equals MA. Never vary. Okay, looks like we're all here. That's good. If you're having trouble knowing where to start, you got to draw a free body diagram, and in this case, the logical thing to draw it for is the light fixture. We know the mass. We want the tension in the string, and that's going to be one of the forces that's acting on the light fixture, so it seems like that free body diagram will involve the force when we do F net equals MA that we want to find out, so that's good. So many of you are working on problem 8. This is the picture if you're having a hard time picturing. Here's an elevator attached to the top. There's a string, 4 kilogram mass string, 4 kilogram mass string, 4 kilogram mass. They're going to have different tensions in these different sections of the string. So I'm going to label this bottom, to middle, tension. Oh, you're right. That's question 7. Lots of you are working your way through problem 7, which requires several kind of different calculations. Let's come together and just do 6. It's pretty easy relative to 7 anyways, once you get the right idea. Here I've got a 5 kilogram mass hung from the ceiling of an elevator. So I'm just going to go ahead and draw my 3-body diagram. The string has some tension in it, and that tension is pulling upward on the 5 kilogram mass. And of course, Earth is pulling down on it, as it always does near the surface of Earth. So that downward weight force vector is equivalent 5 times 9.8 mg. And these don't balance out. I drew them a little bit wrong because the elevator is accelerating upward at 3 meters per second squared. So this whole thing is accelerating 3 meters per second squared. So I'm going to take plus y to the up, just so my acceleration y component is positive. And then sum of the force y components equals MAY. The t comes in with a plus sign. Stop me if you need explanation. The 5 times 9.8, or mg, comes in with a minus sign. We're talking about y components, and it's going down, plus y is up. That's equal to the mass of the thing in the 3-body diagram times the acceleration y component. Since my plus y is up and it's accelerating up, that's a plus 3. And I just solve for t. I got 64 newtons. Any questions on 6? It's sort of an elementary one, although not so much when you're first learning about string things. Now here we've got kind of a beast where there are 3 different masses hung by 3 strings, and it is true the tension is the same all the way through a piece of unbroken string, but when you go through a mass, all bets are off. So there are 3 different tensions here, and well, there are several ways I could break this down, right? I would like, my task is to find all 3 of these tensions, and by the way, the whole thing's moving up, accelerating at 1.2 meters per second squared. Probably the easiest thing to do is to draw a free body diagram for the bottom one first. Why? Because it's only got 2 forces on it. It's got its weight going down, and the only other thing pulling on it is T bottom, right? That string on the bottom is pulling up on it. So if I draw a free body diagram for this one over here, since they're all 4 kilograms, it's hard to tell which one we're talking about, but it's the only one that has T bottom pulling up on it, and it's got a mass of mg, 4 times 9.8. It's accelerating upward, so why not take plus y to be upward? There's steps 1 and 2, free body diagram and my axes, and now I'm ready to do the sum of the force y components equals MAY. T bottom comes in with a plus sign. The 4 times 9.8 comes in with a minus sign because we're talking about y components. That's equal to the mass of the thing in the free body diagram times the resulting acceleration. And in this case, we know that that y component is plus 1.2 because it's accelerating up and I chose plus y as up. You got to be careful about that. If it were accelerating down and I had chosen plus y as up, that number would need a minus sign in front of it. And that allows me to calculate what T bottom is. Apparently it's 44 newtons. How then can I get to T middle? Well, there are several choices. I need to choose an object that has T middle pulling on it. And there are kind of two obvious choices. One is, well, I could choose just this mass, because I already know what T bottom is. So that's a known quantity. My unknown is T middle. That's going to be pulling up on it. Or the other possibility is to combine these together into an 8 kilogram object. Why not? They're moving as a rigid unit, right? Let's just do it that way for the sake of argument. Here's the 8 kilogram object. This is an internal force, so I don't include it. But that the tension here is reaching in from the outside and pulling on that. So there's a T middle going up. And of course, gravity is always reaching in and pulling downward. So that would be an 8 times 9.8. Why not take plus y to be up? Sum of the force y components equals MAY. T middle minus 8 times 9.8. That's the sum of the force y components. And that's equal to the mass of the thing in the free body diagram. That's 8 here, times AY, and my AY is plus 1.2. Can't because I took plus up. And you'll see, well, that's the same thing we had here, except the 4s are replaced by 8, so it's just double the answer we had before when we solved for it. Okay, and then for the top one, well, just, you know, variety's the spice of life. Let's do this one the different way. Let's just do this object there. Just the 4 kilogram at the top. What does it have reaching in from the outside and pulling on it? Well, it's got T top, certainly, pulling upwards on it, but it also has T middle pulling downward on it. And it also has gravity pulling downward on it. Its mass is 4, so its weight is 4 times 9.8. So it's got 3 forces on it. Someone asked in the reading responses, what do you do if you have 2 arrows pointing in the same direction? Just draw them next to each other. Move one over to make room for the other one. And now I do the same thing right here. I choose plus y is up. I have to remember I already calculated what T mid was, the middle tension, so I know that, and therefore I can use the same technique to solve for T top. Not surprising, they get bigger as you go up. Even if it weren't accelerating, the top one's holding more weight down below it than the bottom one is. Questions on that problem? You know, it's sort of like, I probably wouldn't put 3 things on an exam, but connecting 2 isn't too horrible. 3 is just, you know, pointless repetition. But to see that 2 things connected, you could work it out. That's a reasonable kind of thing. Noah. What do you say, class? In this case is, I'm sorry, were you saying that this one and this one and this one?
I'm saying like
or in
T middle and T bottom equal to T top. Add them together.
No, that won't always be true.
Is it true because it's the same weight in each of them?
That won't always be true, but I'd have to, my inclination is that I don't think it will always be true, but I don't have a ready explanation. I'm sure we could come up with one if we thought about it. Is there a reason why you think they would be true?
I mean, it might be in this case because it's equal weights throughout.
Yes.
I mean, it might always be true because the tension on the top is just
Yeah. I don't know. I'd have to think about it. I'm probably not going to think about it right now, but if you want, I can think about it a little bit more. Maybe we can prove that it is true. You know, if I had two light things up here and one heavy thing down there, right, then this tension's going to be big. But these ones will also have to be kind of big, too. So maybe there's a counterexample, right? You said, is T top always equal to the sum of these two? If this is styrofoam, almost no mass there, almost no mass there, then the tension in this bottom, and this is a huge iron chunk, right? We're going to have a huge tension there. It's got to hold up that iron chunk. And let's just imagine the elevator's just sitting there. It's not accelerating at all. This has no mass, so this is going to have the same tension. It's still got to hold up the same mass below it. And this one's going to have the same tension. And so that the top, the middle, and the bottom are all going to be the same. So when we add two of them together, it's not going to add to the third one in that case. So no, that won't always be true. Just yes. So in this, what I'm saying is, I think in this case, it's just a coincidence of the 4, 4, 4. It would not be true if we had a 4, 5, 6 or something like that. All right. Good. Let's go on and just do, or at least set up problem 8 together. It's the same thing, but it just feels a little bit different. And sometimes once you get past that different feeling, the rest of it's pretty straightforward. Here we've got, instead of blocks connected by strings, we've got 3 blocks. Again, we haven't talked about friction, so we're going to put them on a really slick, frictionless surface. We've got a 1 kilogram block, and then a bigger 2 kilogram block, and they're just butted up against each other. And then an even more massive 3 kilogram block. So they're ready to slide on this really frictionless surface. And somebody pushes, maybe with their fingers, very careful to exert a 4 Newton force with their finger. And the question is, well, what happens afterwards? We're asked for the acceleration of the 3 kilogram block. That's part A. And then we're asked for some forces between these, you know. So I might say, well, look, the 1 is pushing on the 2, and the 2 is pushing on the 1, right? They're both butted up against each other. So it's like they're pushing on each other like this as they accelerate and speed up. What are those forces? We're asked about a couple of those. Okay, but first, part A, the acceleration of the 3 kilogram block. Do you think I should do a free body diagram for the 3 kilogram block? Because no, probably in this case, the simplest thing to do is to lump them all into one. So I'm just going to conceive of this because they're moving as one sort of connected whole. They may as well be glued together for all we know, right? They're not doing anything that shows that they're not glued together. So I'm going to take this 6 kilogram object. We've got a normal force. We've got a weight force. We don't really care about those because we're interested in what's going on in the horizontal direction. And frictions would be a horizontal force, but there's no friction here. So the only force that's reaching in from the outside to that object and pushing on it, besides these two, is my finger, 4 Newton force. So we've got a 4 Newton force going to the right. Again, the convention is always to just, there wouldn't necessarily be anything wrong with drawing that arrow over here pointing that way, but nobody draws it that way. It's just we always attach the tails to the object in a free body diagram. I didn't draw it that way at the top because it looks more like I'm pushing it with my finger. Okay, and so that's step 1, free body diagram. Step 2, we're only going to be concerned about plus x, so I won't even decide what y is. And step 3 is sum of the force x components equals max. There's only one force with a non-zero x component, right? This has 0 x component, 0 x component. And that one is a plus 4 newtons x component for this one. Mass of the thing in the free body diagram times the resulting acceleration, and the acceleration is 4/6 or 2/3 or 0.6666. It's SI units, so meters per second squared. That's A. So it's no different than the strings one. It's just that they're moving as a unit in a different way, but they're still moving as a unit, so I can lump them all together. Okay, any questions on A? All right, here's something that sounds a little bit different. Find the force that the 2 kilogram block exerts on the 1 kilogram block. And I was a little bit ambiguous there, I guess, when I wrote this. When I say find the force, I guess the force is a vector. So technically we should specify the magnitude and the direction. The direction is going to be either left or right. The direction's easy to figure out right at the beginning. The force of the 2 kilogram block exerts on the 1 kilogram block as they're butted up against each other and being accelerated in that direction. The 2 on the 1, which way is it going to point? To the left. Yeah, I mean, I've got the answer up there, but right, they're pushing on each other like this. So the 2 is on this side and the 1 is on this side. The 2 is pushing back. The 1 is pushing forward in this direction. The 2 is pushing back. So it's going to be to the left. And then I am just left to find what that force is. To find what the force is, I've got to look for an object to do a free body diagram of where that force is going to be one of the external forces on the object I choose. So certainly, since we're talking about the force on one possibility is just to choose the 1 kilogram mass. Another possibility is to choose the 2 kilogram mass, but unfortunately that has an unknown force over there on that side too, so that's probably not a good idea. Or I could choose the 5 kilogram mass over here because it doesn't have any forces from that side, and the force I want is still pushing on the 5 kilogram mass. It doesn't really matter, but it seems like the 1 is the simplest choice. So for B, I'm looking for the force of the 2 on the 1. So let's draw a free body diagram for the 1 kilogram. Of course, it's got a normal force. I'm not going to think about it too much. It's got a weight force. They're going to balance each other out in this case. And the 1 has 2 forces on it, right? I'm pushing on it with a 4 Newton force to the right, but 2 is pushing back on it in that direction. So the length of this arrow I'm going to label as F2 on 1, just so I remember what it means. It's the magnitude of the force that 2 pushes on 1 with. That's what F2 on 1 means. Okay, I've already got an x-axis here. Nothing interesting going on. If we did sum of the force y components equals MAY, we would say AY is 0, and that means the normal force balances out the weight force in this particular example. That's not too hard to see, but we're interested in the x direction where it is accelerating. So let's do the sum of the force x components. I'm going to choose the same x-axis as before. 4 newtons, that comes in with a plus sign. The F2 on 1 comes in with a minus sign. Remember, F2 on 1 means how big that force vector is, but it's a negative x component when treated as a component. Okay, and the other two have 0 x component. That's equal to the mass of the thing in the free body diagram. That's 1 kilogram times the A, and all these things are accelerating at the acceleration we found already, so that's 0.6667 in SI units. And I can solve for the magnitude of F2 on 1. What did I get here? 3.33 newtons. Well, in this case, I've tried to phrase the question, and I often do this in a way where I don't need to know what your coordinate system is in order to check whether your answer is right. So if this were an exam, I might just say, find the force magnitude. Or I might say, find the force magnitude, and also separately answer with the direction. In this case, the choice is being left or right. And you would have to choose one of those or fill in the blank there after you've done the work. In order to know what a minus sign means, that sounds like you're giving me a component, and then I would need to look at your coordinate system. But when someone says a force, usually that's different than a force component. So if I'm asking for a force, that doesn't mean I'm asking for a force component. Of course, I know what you mean, but it's always best to answer it in a way that sort of speaks the same language. And a force is different than its components. without doing C now, how would I find the force that the 2 kilogram block exerts on the 3 kilogram block? What might be a good subject for my free body diagram here? What was that? The 3, yeah, seems like the simplest one, right? Without solving it, I'll just say, here's the 3. I've got a 3 times 9.8 mg going down. I've got some normal force that I'm not really concerned about. And I look at the 3 and I say, what is pushing on it in the horizontal direction? Again, there's no friction, so the floor is not pushing on it at all. The only thing reaching in and pushing on the 3 is the 2 from there. So we've got an F2 on 3, pushing on 3 to the right. And we can just solve for it by, choose plus x, say, to the right, and sum of the force x components equals max, same a that we had before. Anybody want to see part C? It's kind of more of the same, but, I know this stuff's still kind of new, but hopefully you're getting, now that we have spent much time doing this, the rhythm of this, which is choose a free body diagram, choose an object for a free body diagram, draw all the forces, choose the axis, and then F net equals ma components to solve for. Maybe the acceleration is your unknown thing. Maybe one of the forces is your unknown thing. We've done both those kinds of things. No, because my finger is not directly pushing on 3. My finger, if I push harder over here on the 1, that's going to cause 2 to push harder on 3. But I've already taken that into account right here, right? So it's all baked in there. You don't want to say, just because I'm pushing something 10 boxes over, that isn't a direct force on the one that's at the front of the pack. My finger is a contact force, and so only the thing that it's pushing on, it should only appear in things where that's part of the free body diagram. Good question. That's a common kind of mistake too. All right, that was a lot of stuff on connected objects that are more or less moving as a unit. Okay, let's go back and look at the slides again. Let's see if I share my screen and then go back to my slideshow. The next problem that we read about, and I'm just going to quickly flip through it, and then we'll do a different kind of pulley problem, involved something of kind of idealized pulley. In the same way we're using idealized strings, this had us, you can imagine if I loop 2 masses over a pulley like this one's more massive, this one's less. This one's going to start falling down while this one gets pulled up. Hopefully that's not too non-intuitive. So we need to know some properties of pulleys. So let's add on to the stuff that we discussed earlier. We're going to assume for now that this pulley wheel is massless. In other words, it's not like a heavy iron barbell plate where, you see the football guys in the gym and they're putting these huge things on there. If you took that and tried to spin it, you'd have to give it a big heave to get it going. Right? The mass plays a big role there. There's a lot of inertia to starting it spinning. So in this case, we're going to assume the opposite. This thing is effectively massless compared to the masses of the things that are, causing the motion at the end. So we'll call it a massless pulley. Another thing that might affect how hard I have to push on it is if there's any friction, like a grinding in the middle. It's not a very good bearing in the middle or something like that. Something that really grinds a lot as it's spinning around in the middle. We're going to assume that's not the case. So there's no friction associated with that rotation. For now, when we get to discussing rotating rigid objects, we will relax the first assumption and sometimes say we've got a heavy plate, and that plate has a uniform thickness all the way across, and we'll learn how to deal with that when we get there. But for now, we're going to assume that these are massless and frictionless pulleys. If that's true, one thing that we're going to use right now, and again, this won't be true later. If that's true, if there were any difference in the tension in the strings on these two sides, if my pulley is both massless and frictionless, it has no resistance to moving at all. But if something's massive, it takes a while to get it going. But if it's massless, it's happy to just be shoved or rotate as fast as you care. So if this is massless and frictionless, if there were a bigger tension on this side and a smaller tension on this side would immediately win out and cause this thing to instantaneously adjust until the tension's balanced. I don't know if that's an intuitive argument or not, but if I'm pulling harder on one side than the other, it's going to cause it to rotate. If it truly is massless and frictionless, that rotation takes 0 time whatsoever. In the same way that if I had an object, there's no such thing as a truly massless object, but I imagine an object that's really light, and I take 2 fingers, right, and I say, this thing's floating in outer space. I push on one side with a bigger force than I push on the other side, and I try to push them with my fingers so I can't really move with it. It's going to immediately start moving to the side with the bigger, moving away from the bigger force side. And that's going to cause my finger on the other side to probably exert a bigger force, and the one I was pushing with it is running away with to exert a smaller force until they balance. And so it's going to be hard not to balance in that case. In any case, when we say massless, frictionless pulley, we're always going to assume the tensions are the same on either side of the pulley. That's not going to be true with massive barbells. The example I gave in, if this were a massive barbell, we're not going to treat that case right now. But if it were, it's really hard to get going. And I imagine I put a big chunk of iron over here, and on this side I have a little piece of styrofoam. Hardly weighs anything at all, right? And then I let it go. Well, this side's going to start falling, and this side's going to start rising. But it won't fall too fast because this thing is really hard to get going. It's super massive. It doesn't want to start spinning immediately. It takes a while to get up to speed. So it's going to go down, and you can imagine this is going to have a huge tension in it, right? Because it's supporting the weight of this thing, keeping it from going into free fall. So the tension is going to be huge over here. But most people have the intuition that if you have a little piece of styrofoam hanging on the end, the tension over here would be almost 0. So the tensions in that case won't balance. But for now, if that thing isn't a big barbell plate, we're going to assume the tensions are always the same because it has no resistance to immediately rotating over. Okay, now the process here is important. So let's just at a high level review this. So in this case, we've got these 2 objects looped over the pulley, idealized string, light string. And we want to know the acceleration. And then there's a little kinematics problem tacked on to the end. Both of these things are going to accelerate at the same rate, but they're not going to accelerate in the same direction. The 1.2 kilograms is going to accelerate downward, whereas the 1's accelerating upward. So it's a little bit more complicated than what we did before because they're not moving as a rigid unit anymore. I've got 2 pieces that are connected. The magnitude of their acceleration is going to be the same, but the direction of their acceleration is going to be different. So I can't easily lump them together into one object. So what we're going to do is actually do a free body diagram for each of these separately, 2 separate free body diagrams, and then I've got to make sure that I won't go into the details of why, again, because I talked about it in the video. You've got to choose what's called a consistent coordinate system for your free body diagrams, so that if one of them moves in the positive y direction, you better choose a coordinate system for the other one so that it simultaneously moves in the y direction when they're moving as a rigid unit. And when one moves in the negative, the other one better move in the negative. Okay, so when I draw my free body diagrams, maybe for the one on the left, I'll choose plus y is up. That means once I've made that choice, I have to choose plus y down for the one on the right. Otherwise, you'll get horribly confused and get a minus sign missing and things. Okay, so here's a free body diagram for the 1 kilogram one. Only 2 forces, the tension and its weight, and I've already chosen plus as up. Okay, when I write down F net y equals MAY, nothing surprising happens, but unfortunately, I have 2 unknowns, the tension in the string and the AY. I wanted the AY, I don't really want the tension, but I'm not there yet, so I'm going to put a half box around it and say I'm going to hold on to that equation. Let's go over to the second free body diagram. Again, it's kind of simple. Tension's pulling up on it. Its weight is going down. This one, since I've chosen plus as up and the string is looped around like that, I have to choose plus as downward in the second free body diagram. And that's because, well, when I write down F net y equals MAY, I am going to be really tempted to use the same symbol. In fact, I want to use the same symbol for the acceleration. And I want it to, if this is the same symbol, it means exactly the same number goes in there. If this one's positive, this one's got to be positive too. Otherwise, it shouldn't be the same symbol. And since when this one goes up, this one's going to start accelerating downward, they'll both be positive in the same situations. If one goes in the negative, the other one will go in the negative. So they'll both be negative at the same time. And I'm justified in using the same symbol. That's why we're choosing the crazy, what look like non-obvious directions, where I'm switching my choice for which way plus y is. That's so I can use the same symbol there. And then I've got two equations and two unknowns, and it's, a little bit of a pain. You go into substitution mode. I want to know ay. I don't care about t. So I solve for t in one of the equations, maybe the second one. There it is. And then I plug that whole expression in for t in the first equation, remembering there's a minus sign in front of it, so I have to subtract off both of these because we're subtracting off all of these. And when you do that, nothing interesting happens. You get an equation that only involves ay. You have to collect together the ay's on one side and all the non-ay stuff on the other side, and you can solve for the acceleration. What I want to do now, and then, well, I guess I should mention that there was another problem at the end here, which was if released from rest, how long does it take the 1.2 kilogram block to fall 0.8 meters? That means I know a distance and I want to know a time. Sounds like we should do y versus t with that quadratic equation. And we've just solved for the acceleration to put in there. We don't put in that 0.8. Okay. So let's go see if the problem we're going to work on is in just a second. But this is an important voting question that was in the slideshow for the videos that you watch. How does the tension, so someone's holding on to this. Most people, this is a frictionless plane right here. Holding on to it, it wants to slide down, then they let go of it. And of course, it starts accelerating, right? This thing starts going down there, this one starts falling. The string stays taut during that process, so they sort of move with the same acceleration. How does this tension, T, in the string right here relate to the weight of this mass? I've got the answer highlighted there, so it's not much of a mystery. But the sucker answer is, and which is also the most common answer people give, is that they're equal because, forces always balance out. You got a bunch of vertical forces, they got to add to zero, right? When is that not true? It's not just when it's moving, but it's got to be accelerating, right? Moving just at a constant velocity would still have them balanced. But if this is going to accelerate down, the weight has got to win over that backwards T force. Right? It's got to be bigger than it to overcome it and make the net forces in the same direction as the acceleration. So if it's accelerating down, I think that's pretty clear. I'll release it from rest. It's not going to stay at rest. That's going to start going down. Weight is bigger than the tension, or the way it's phrased here is the tension in the string is smaller. And somebody asks a reading response question as, I think, how this tension is related to this tension. And if I said it's a massless, frictionless pulley, I didn't really hear, but if it's a massless, frictionless pulley, this would be the same tension as there. That's the only case we've talked about so far. So for the only problems we're dealing with so far, the tension would be the same on the two sides of the pulley. Okay. I don't think I have a printout of this problem, so you're just going to have to kind of do it on your paper. But I just pulled a graphic off the web that was, perfectly simple, comparable problem. Maybe, who knows, maybe it's even a little bit simpler than the previous one. I called it problem 11 because I added on some friction problems to our worksheet, and those were problems 9 and 10, so then in my mind this was problem 11, but whatever, it's a pulley problem. So M1 is 5 kilograms up on top there. It's sliding on a frictionless surface, so that's a really slick surface that it's on, horizontal. connected by a string looped over a massless, frictionless pulley. The string is massless, all the usual ideal aspects. If released from rest, what is the speed of M1 after it has moved 0.75 meters? Well, that, again, to me, should be sounding to you like a kinematics problem. If I only knew the acceleration, I might have an idea of how to start the kinematics problem. So it seems like if I want to answer this, the first thing to do is to find the acceleration. That's what we were doing in the previous example with the one that was shown in the video, with the loop vertically over it. So try to set this up. I'll give you a couple minutes to do the free body diagram for this one, free body diagram for this one. Consistent axis directions, that means, for example, if I take plus x to the right for this one, I better take plus x down for this one. That's what a consistent axis direction is going to mean here. When they move as a unit, they're both moving in the same positive coordinate direction, or if they move in the negative, they both move in the negative together. I think this one works out a little bit algebraically simpler than the one we just looked at. threw this one in right before class, so I don't have numbers to give you. Calculate it as we go. Let's just try it together, because you either have the sense that you're on the right track or maybe not. So here is my M1. I just put in the masses in there for my own sanity. What forces are on this M1 that's up on top? Well, the string is certainly pulling it in this direction. We'll say the unknown string tension is T. I don't really want to know T, but it's a force, so I got to label it with something, and hopefully I can get rid of it. Of course, there's also a normal force from the table. There's no friction force, but the table's pushing up on it. And there's a weight force. They're not going to really come to anything in this problem. So that's what the free body diagram for the upper left one looks like. And then the one that's hanging is a little bit simpler. It has the tension pulling up on it. The same tension, because we have a massless pulley. And its weight pulling down, too. Step one was to put in both free body diagrams for the independent parts that aren't moving as a unit. Right? It's just a little bit more complicated. Step two is consistent axis choice. Now, this one is moving in this direction while this one goes down. So I'm going to take, for this free body diagram, plus x in that direction. For this one, plus x in that direction. I could have called it y. It doesn't really matter. And if I wanted, I could choose a y direction too, but we don't really specify it. And now let's write down for each one of these choices of x. Sum of the force x components equals MAX. The only force with a non-zero x component is 0 x component, 0 x component. This one T is the magnitude of the thing. That's the mass of the thing in the free body diagram times the unknown acceleration. And I want to know that acceleration, but I don't know T. So let's hang on to that. That's a little bit simpler than the one we got in the other problem. And now to here, sum of the force x components equals MAX. Here we have the 2 times 9.8 comes in with the plus sign, and the T comes in with the minus sign. That's equal to the mass of the thing in this free body diagram. That's 2 times the same AX. That AX means exactly the same thing because I chose that consistent positive axis direction. And I want to know AX, I don't want to know T, and it's pretty straightforward to start out because I've already got to solve for T. I don't need to solve for T. So this one comes after substituting 5AX for T. I get 2 times 9.8 minus 5AX equals 2AX. And then whenever you have your variable that you want to solve for appearing in more than one location, you put them all on the same side and combine like terms, right? So I would add 5x to both sides, so that means I get a 7AX is equal to 2 times 8 times 9.8 7. 9.8 over 7, 2.8 meters per second squared. It's always a good idea to sort of, just sanity check your numbers because I might have flubbed up my calculator, but this makes some degree of sense. That M2, if it weren't for the string holding on to M2 as it's dangling there, the string were cut, it would want to accelerate downward at 9.8 meters per second squared. That it would be in free fall, right? And the M1 connecting to the string to M2 is slowing it down so it can't accelerate as fast. And this is reasonable to between 0 and 9.8. So that makes some sense. I feel good about it. All right. And now we're in a position. Any questions about the acceleration? Quickly do a kinematics problem, right? What is the speed of M1 after it has moved 0.75 meters? I'm making the assumption that it actually has enough room to move 0.75 meters before it runs into something, but let's assume that it does. What kinematics equation do we want to use if we want to know its speed after it's moved 0.75 meters? The x versus speed, the vx versus speed, or the one with the vx squared? Squared one, because it involves what I want to know, what I already know. Thank you. To a, it's really the rest of the initial velocity x component is 0, and therefore its final speed would be root 2 times ax. Again, it's kind of a unfortunate thing that a lot of students like to put 9.8 in when they see an acceleration. We did all this work to calculate that acceleration. Ax in my coordinate system is 2.8, right? This one's accelerating to the right, this one's accelerating down, both at 2.8 meters per second squared, times delta x in speed when it's moved by 0.75 meters. Calculate that. Any questions on that one? So much to do. I would like to talk about friction and maybe do one friction problem today, and that will just sort of close out our discussion for chapter 4. If you need to get up and stretch for a minute, let's do that. Then we'll do a high-level discussion of friction. We'll do a problem or two with friction, and then we'll be done for the day. Except for office hours. So remind me, I looked at the doodle poll. Maybe if the person is in here, somebody signed up for next Thursday, and I don't remember who the name was. That is the day, is it you, Hamungi? Which is a fine day to do it. It happens to be the day after our exam, so I just want to make sure you knew that. You're welcome to change your mind on it, but so on that day, I'll just log into the computer, get my stuff all set up, and then you can open up a web browser or bring a thumb drive and get your presentation, however. I don't know that I have a good explanation for why. I mean, a lot of people just have their inherent things that they enjoy, but I fell in love with it in college. I didn't really, I mean, I took physics in high school. I didn't really like it. And then this university I went to, you had to declare a major as a first year, unlike a lot of small liberal arts schools. So it was an engineering kind of school, and I declared aeronautical engineering. And I mean, the aeronautical engineering classes were fine, but, you know, nominally you'd be working at Boeing or something like that. And we had to take of course, introductory physics for 3, we were on a quarter system, and then you had to take modern physics, and I just fell in love with modern physics. And it was hard to switch between majors there because you had to be accepted. If you wanted to switch, you had to be accepted into a new major. You couldn't willy-nilly change majors. So I had been accepted into aeronautical engineering, which was quite impacted. It was difficult to get into, and they said, you're welcome to switch into physics because not many people are going into it, but you are not going to be able to switch back in. But it ended up working out well. I mean, you got to do what you love, so. No, I think physics was the best fit. Yes, well I mean, you don't see many schools where you can't be undeclared, but there you are not allowed to be undeclared. You had to, and every department had a different standard for how they accepted people. So you were different GPA cutoffs and everything depending on what you wanted to major in. And you had to know. Now you could switch, but you had to be accepted into the other major after you were there. Yeah. I was a music minor too, which was kind of a challenge because I was not someone who played an instrument. And of course you had to have some practical instrument study while you were there. So I chose piano. Now I had taken it for like a year when I was a kid, but I remembered nothing. And we would sit in this small room with a grand piano, and it was a class. It wasn't just one-on-one lessons. So I think there were probably 8 students in there, and the professor, and we would all sit around the grand piano, and one by one we would go up and sit next to the professor and play our pieces we were working on, and he would criticize you while everyone else has nothing to do but just sit there. So I was highly motivated to go in those practice rooms, and I practiced so much. After the first year, I was like, I'm done with my, instrumental stuff. I took a bunch of theory classes and history classes, but I took the bare minimum of performance. But that was, yeah, I mean, it didn't come to anything because I never did anything with music, but it was a lot of fun. Yes. All right, let's go to the last topic. And, this chapter just has a lot of topics. They all fit together because we're doing free body diagram, axes, F net equals ma. But this is our last force for now. We're going to talk about gravity in detail in the next chapter. But friction's the last force we treat in this chapter. And the first one, there are 2 different cases for friction. Kinetic friction is when an object is sliding on a surface and the 2 surfaces are moving with respect to each other. So it's like the 2 surfaces are grinding against each other. I mean, there's another sense in which we have friction, and if I tilt this a little bit, it doesn't roll off. Why is it not starting to move? Well, that's because of friction too, but we're going to call that static friction because the brass mass in contact with the cardboard is not moving. There's no grinding going on. So that's going to be a different case, and we'll talk about that shortly. But for right now, we're talking about when things are 2 surfaces are sliding against each other. So here is a box. I'm imagining it's moving at a constant velocity. It doesn't have to be. It could be accelerating, but it's grinding against the table, and there's some friction. So we're applying a force to drag it to the right. What we're going to call kinetic friction, that's what this little K is here, Fk, is going to go back in the opposite direction. And of course, if what I'm saying is true there, that it's moving at constant velocity, that means there's 0 acceleration, and these 2 forces better exactly balance out. That's how I drew it here. Similarly, the weight and the normal force balance out because it's not blasting off or burrowing into the table or something strange like that. So what are the properties of this force? In other words, do I have to apply a huge force to overcome a huge kinetic friction force, or do I hardly have to push at all? Well, it depends on a couple of things. Of course, it depends on the materials, both the brass here, and when I say the materials, we're also including kind of how polished the surface is. We're going to throw that into the materials aspect of it. So if I make this rough versus very smooth, that may change what I'm calling the materials. And the materials on both sides, both the brass and the cardboard. So, you know, glass on glass, Teflon on Teflon, there's not going to be a big friction force. But if you do like rubber on rubber or some really sandpaper on wood or something like that, it might be a big friction force. So it depends on the materials at the sliding interface. It also depends on the normal force at the sliding interface. In other words, the harder this mass is pushing against the surface of what it's sliding on, right? I have to push with a small force. If I push down and make the normal force bigger, then I really have to push to move it along, right? Depends on the normal force. The second pair of bullets here is not something absolute, but it's just a very rough and ready approximation to make our law simple. These are not things that are fundamentally true. It's sort of independent of the shape or the area of the sliding. The claim is, and several people ask questions about this in the read responses. Can't really turn this on its side, but maybe if I put the box together again, and I'll put this on it to give it some more mass. The force I would have to apply to overcome that friction force, which is sort of a measure of the friction force to push it along at constant velocity, is about the same as the size of the force I would have to push with to keep it going at constant velocity this way. Now that's not exactly true, and generally it's going to be a little bit bigger with a bigger surface area. Substantial effect. And on Tuesday we will do a friction lab where we actually measure this, turn things on their sides, change the surface areas, and change the materials as well. This one doesn't necessarily square with a lot of people's intuition. You know it's not exactly true. There would be no reason that drag racing cars would put those huge wide tires on them if, a bicycle wheel would do just as well. Right? The mass of the drag racer would be just about the same. Why would you put those huge racing slicks on it if the area doesn't make a difference? It does make a difference, and this is just treating friction in a very simple way. But it's more or less independent. In other words, the force doesn't change. The force that friction exerts doesn't change by much when I flip it on its side. We'll maybe talk a little bit about why that might be the case. It also, not exactly, but it sort of doesn't depend on the speed at which I'm sliding it. So if I'm pushing it at a very slow speed, overcoming friction, or maybe I push it at a really fast speed, overcoming friction. Friction pushes back with about the same force, but that's not necessarily something that's exactly true. But we're going to create a very simple law here that takes just the top two things into account and pretends that it's not dependent on the other two. So this tells us, I might have given you a problem already with friction in it where you would have just been told the friction force, but this tells us how to calculate the friction force. The friction force is proportional to the normal force. So if you, and I guess in Giancarlo he would write this as F sub n. So, but this is the normal force. So if you double the normal force, you're going to double the friction force that is being exerted when two surfaces are sliding. The constant of proportionality here, this is the Greek lowercase mu. It looks like a U with a little tail on the left end, but it's the Greek M. And it's got a K to remind us that we're talking about kinetic here. We're not talking about static friction where the surfaces are stuck. It's called the coefficient of kinetic friction, and that depends on the materials at the sliding interface. So large coefficients of friction mean it's really hard to push the two surfaces against each other. With small coefficients of friction, it's going to be really easy. That's like Teflon on Teflon or something like that. So this tells us how to calculate with it, and it's pretty easy to use and hard to misunderstand this one, unlike the static friction one that we'll talk about shortly. But there were several questions about friction that I kind of threw in here. Let's just see what they say. Not really sold on the fact that friction is independent of the shape of an object. If an object has ridges on the bottom, it would be a lot harder to pull than an object that has a flat shape, or would it not? Yes, that's true. If an object has some little ridges or ribs on the bottom, that's going to make it harder to drag across another surface, especially if both surfaces have little ridges on them. And you know, if you look with a magnifying glass at a cardboard box, there's all sorts of little pieces of wood, things that are sticking up. You know, it's not at all a flat surface. We're going to throw all that kind of stuff into that coefficient of kinetic friction. So it's going to be treated as part of what the material is. A rough piece of material, we're going to think of as being a different kind of material than a smooth piece of material. So I might have my brass mass here and I've polished the bottom of it, and then somebody comes along with really coarse sandpaper and roughs it up. Yeah, the friction force might change quite a bit. We'll just treat them as different materials. So we won't really treat that as changing the shape of the object if we just put ridges on it. Okay, but someone's still asking about it, I think, in the second one here. I'm confused as to how friction is the same when a book is sliding on its spine when it's sliding on its cover. How can they be the same? The surface area is the cover is way more than the spine, meaning that more of the book is coming into contact with the surface. The idea is kind of this. So we'll pretend this is the book, and here's the spine, and here's the cover, like that. And I'm going to add a certain amount of mass to make it substantial. When there's a certain amount of mass that's pushing down, so the downward force is the same in both cases. But in one case, it's spread over a much larger area. And we'll talk about, well, maybe we won't, because I don't know if we'll have time this semester. We might talk about pressure at the end, which is force per unit area. In any case, the force is spread over a larger area here and a smaller area there. It's spread over a really small area here. And what that means is, well, you know, what looks like a flat surface isn't really flat. It's got all sorts of little variations in it. And if I really mash that into the surface, I'm allowing pieces of this material to get a lot closer to the material on the table and therefore form chemical bonds with it. So if I don't push down much on it, maybe only the parts of it at a microscopic level it's going up and down, and only the little ridges are sticking down and touching the table, and they form bonds, very weak bonds. Whereas if I push down, I really mash it into the table, and maybe more of that stuff gets deformed and it actually bonds over a larger surface area. But that depends on the pressure. The local pressure is what's going to determine that, not the total force, but the force per unit area. And so it's not, I mean, I'm not saying this is an airtight argument, but what it's saying is, yes, when I push down with the same force, I'm getting less deformation at all the little parts on the bottom of this, but there's more of it. And so it adds up to about the same amount as the same force down, but spread over a larger area where I have more deformation on the bottom and therefore a tighter bond, but there's less of it to work with. So they kind of balance out that way. Sort of. It's not exact. I always thought that smaller skis made you faster because less surface area and thus less friction. Is this reasoning wrong if friction is not dependent on the area of the sliding surface? It's not wrong. I mean, it's sort of roughly correct to say that it doesn't depend on the surface area, but it does depend on the surface area. But, you know, if it really strongly depended on the surface area, now I'm someone who skied when I was younger, but I'm certainly not a competitive skier. Is it not true that downhill skiers have really long skis? That's my memory. Slalom skiers have shorter skis because they need to be more agile. But if you're in the high-speed downhill skiers, don't they have like really long skis? And if that made a big difference, I know that makes them more stable, but if it made a big difference, they would go with shorter skis if it were slowing them down that much. I'm sure they would. I don't know. So I think it's not a big effect. And so in this case, having the longer skis that give you that much more stability forwards and backwards far outweighs the advantage you get from having a slightly smaller friction force. It's roughly independent of the surface area. I understand that the constants for kinetic and static friction determine the friction force acting on an object, but what exactly is that number? How is it calculated? Does it have units? And if not, why? It doesn't have units, and I neglected to say that on this slide, but we can see that it is a dimensionless or unitless thing because this is a force, as units of newtons and SI units. This is a normal force, so it's also newtons. And so this thing must be unitless or dimensionless. So it's a pure number. It's like 0.3. There's no units associated with it. And it just tells you, some constant of proportionality between these two. So it's saying, yes, it's true. The bigger the normal force, the bigger the kinetic friction force. But exactly how are they related? Are they related by a factor of 1/3 or 2/3 or what? That mu k is telling us that. Anybody have more questions on that? I'm not sure if I addressed the full intent of that. But no, it's unitless. And it's just telling us how sticky those surfaces are. Stickier the surface, for a given normal force, you're going to have a bigger friction force, kinetic friction force. Okay, static friction force is always more confusing to people. So that's why I'm doing it second, even though it sounds like it would be simpler. Here is an object that's not moving. In other words, if I've got a pretty massive object here, this brass mass, I put it on the table, and I push from the side with a very puny force. It doesn't start accelerating. It just sits there, right? I'm hardly pushing on it at all, but I am pushing on it. What that means is, because it's not accelerating, the static friction force must be pushing back exactly as hard as I'm pushing forward because it's not accelerating. Those two, they're the only horizontal forces that could be there that I can see, and they must be balancing out, right? Now, you can't see how hard I'm pushing, but I'm going to push a little bit harder. Still pretty puny, but I'm going to do twice as puny, or double the puniness I had before, and still not moving. Okay, so that means the static friction force must have gotten bigger, that friction force. So the idea is the free body diagram looks very similar to the one for the kinetic friction, but nothing's moving here. If I push with a small applied force, the static friction force is small and in the opposite direction. If I push with a bigger applied force, the static friction force is bigger in the opposite direction. But that doesn't just keep going forever. So one of the rules you can think for static friction force is, under normal circumstances, if something's just sitting there, the static friction force balances all the other forces that are parallel to the plane. I was doing an example with just one force, but I might have competing forces plus friction, so there could be several forces at play there. But it can only push back so hard. There's a breaking point at which, if I push hard enough, it starts moving. Ooh, this is rubber, so it's really hard to get it moving on there, but if I put it on this plastic part, if I push a little bit, it doesn't go, but if I push hard enough, I can get it to move. We all know that kind of thing. So there's a second law that doesn't talk about this case where it's just sitting there, but rather tells us what the breaking point is for that friction force. And that's what's really interesting. This is important, but we're not at the breaking point of the friction force. When you're at the breaking point, we would say, I'm applying a bigger force, and this is the maximum static friction force that it can push back before it breaks free. And then it starts sliding and grinding against the surface, and we're not talking about static friction anymore. We're talking about kinetic friction. So this second law is going to tell us, yeah, for a range of applied forces, the static friction force just balances them out. But at some point, it's going to give way and start sliding. The maximum it can push back before it slips depends on the same thing that the kinetic friction force does. If you have rubber on rubber, it's going to be a much larger force before you get it to finally start going. And if you have a really heavy object, you're going to have to push a lot harder. In other words, friction can push back a lot harder before it gives way, as opposed to a not so massive object. And again, it's roughly independent of the shape or area of the sliding interface. That's not an exact rule. That's just a rough rule. Tends to be that bigger areas give a very slightly bigger force, but not too much. Here we don't have to talk about the speed because it's not moving, so there's no velocity dependence to be talked about here. So the confusing thing is that this law that we're making here that tells us about the breaking point for static friction looks almost exactly the same as the one for kinetic friction, but it means something totally different. Okay, it's saying The biggest force, that's what this max means, that static friction can push back with when it's just about to break free. How big can it hold on when it's, if you pushed any harder, it would break free? How much of a force can it push back? That maximum force is a coefficient of static friction that depends on the materials, and it also depends on the normal force, right? Bigger, heavier object, bigger normal force, and that means you have to push harder to get it to break free. That means friction's pushing back harder. But notice, this isn't always acting, right? If I say, suppose we know the normal force from this on here, and we know the coefficient of static friction between these two surfaces, and I say, here's the sucker question that people always fall for until they've seen it a couple of times, and we'll practice with it. This thing's just sitting there. Calculate the magnitude of the static friction force. And a lot of people will just run to this equation and say, oh, they gave us the static friction force, and we already figured out the normal force from something else. I'll calculate it. That's not the static friction force, because there's no indication that this object was at the breaking point. It wasn't just about to slide. I have to give it a bigger force before it starts sliding, but who knows? There's no reason to believe that it was just about to break free. So that second law there that looks very much like the kinetic friction force, which really does apply to lots of different things. This one we only apply when things are about to break free. Okay, here were some examples, and I just want to talk about two of them. Hockey puck sliding towards the goal, that's an example of kinetic friction because the two surfaces are grinding, maybe not too much because it's ice, but still moving relative to each other. When you move a comb through your hair, the two surfaces are moving relative to each other. Walking superficially sounds like something's moving, but I don't want my feet to be sliding with respect to the floor while I'm walking, right? Then it would be like, you're on the ice and losing contact with things. We want to walk in almost all cases to keep our feet at rest with respect to the floor. My body's moving, but my feet are staying attached to the floor even though I'm moving through it. So that's a case of static friction acting there. Car driving, again, it sounds superficially like there is movement, but when you think about the tires are coming down against the road, and their kinetic friction would be like they're sliding against the road like that. That's like you're peeling out or sliding like that. You're screeching to a halt in your car. Most of the time, we don't drive that way when we drive a car, right? We try to keep it so the wheels don't spin relative to the road. So even though they are moving with respect to the road, this point that comes down in contact with it is not sliding backwards or moving forward relative to the road. It's coming down sort of just touching it in a way where it's coming and touching it at rest. And then it lifts directly up from it without sliding against it. So we don't normally drive a car by peeling out or slamming on the brakes so you skid to a stop. So that would be an example of static friction. Now, the book, I think, talks a little bit about rolling friction, which is a more complicated concept. But certainly, car driving is much more like static friction being involved than kinetic friction. It is true that there's a time scale here. The tire chemical bonds do take a certain amount of time to form. Now, it's a very short time because molecules move really fast, but this thing's coming down and touching, and it's got to really have enough time to form the bonds there. And so there might be a speed-dependent effect. I actually don't know that much details about it. A few questions, and then we'll do some examples. Does static friction always occur before kinetic friction when using a force on an object? I mean, I'm not really sure how to interpret this, but my answer would be no. In this case, it would, right? First static was involved, and then kinetic friction, right? First they weren't grinding, and then they were grinding. But, I could take this and, say, I'm just going to start it with my hands sliding on the table. And then it comes to a rest. In that case, it was kinetic first, and then it sort of got attached to a static situation later. Is static friction coefficient greater? So why is the static coefficient greater than kinetic friction coefficient? Well, I mean, I guess there's two ways to answer this question. One is there would be some sort of almost logical contradiction if the reverse were true. In other words, suppose that the kinetic coefficient were bigger and the static coefficient of friction were smaller. Then, if this thing broke free and started moving, suddenly the kinetic friction force would be bigger than the former smaller static friction force, and that might cause it to slow down and stop again. So it's like it couldn't even move in that case, because as soon as it breaks free, there would be a bigger force going backwards, and that would slow it down and stop it. I'm not even sure how to think. Another way to think about it is, look, when something's sliding along a surface, there are chemical bonds being made and broken. Parts that are protruding down and protruding up are bonding and breaking. The bonding at one time that determines the force. And if I allow this thing to sit here, there's a whole bunch of bonds that form and sort of are stable like that. Whereas when I'm causing them to constantly form and break, you just at any one time just don't have as many bonds solidly formed. Come to rest and form their nice bonds. Whenever at least for the macro, if nothing's pushing on it, there's no horizontal. Whenever I try to push my jet, how does that work? How is the static friction created? Yeah. Forming really tight bonds, and probably as time goes on, your jet sits in the same place for weeks. Bonds are formed really tightly. Oh, I guess we won't have time to do that. You get a lot of strong bonds there, and then you've really got to push hard to break it. Not only is there a big normal force, but I've got really tight bonds, and then all of a sudden it gives way and sort of goes forward. So I'm going to stop there, and we'll do these last two example problems that I haven't passed out yet, that I have printed out on Monday, and that will be the end of the stuff that's covered on next Wednesday's exam. Feel free to bring more questions having to do with the exam on Monday and Tuesday. Tuesday, we're going to do a lab associated with friction, but I'm happy to work some time in that day too for problem solving or whatever. Expect some sort of random collection of problem solving stuff associated with these three chapters, chapters 2, 3, and 4, that I will email to you, if not right now, it depends on how long office hours take, then by tomorrow morning, I hope. And if you don't get it by tomorrow morning, please email me and remind me. That just means I've forgotten. Have a wonderful weekend. I hope you have some leisure time. I know there's not much of it, especially at this time. We're in exam season now, and everybody's having their exams at the same time, unfortunately. A comedian, what do you mean? Sure. I'm just going to stop this recording because we don't need it on anymore.